In Lecture 9, we're going to be looking at some of the properties that our different trig functions have. For example, we're going to look at the domain and range of each of our trig functions, which means what values we can plug in to our trig function values, what angles, that is, they are valuable, or that you can evaluate those trig functions for. And the range is the output of those trig function values. By the way, this should read, and sorry for the typo, the domain and the range of the trigonometric functions. We're going to talk about the periodic nature of our trig functions, that is, they repeat themselves after you go through a full rotation. Some of them actually repeat themselves after a half rotation. And then we're going to look at the signs of trigonometric functions within a given quadrant. Turns out we can, without having been given the coordinates, use some trig function values to find the values of other trig functions. But all of that fits under the category of trying to find and identify certain properties that trig functions possess. Let's first consider the domain and range of each of our trigonometric functions. Again, recall that domain of a function is the set of all inputs. Whenever we first started talking about functions in our early sections or our early lectures, we talked about domain and range of functions. Domain being those values that you are allowed to plug in, for which the function has a value. The range is the set of all outputs. That is, what points, what values can we get to once we plug an angle into a trig function. So first let's talk about domain. Okay, domain means what can we plug in. For sine and cosine, we can actually plug in any angle. Now the reason why we're not restricted in any way is we remember that sine of an angle is just the y coordinate and cosine of an angle is just the x coordinate for the coordinates on the outside of a unit circle for a given angle. So if theta is any angle, now notice if you take any angle, no matter where it is, no matter how big, no matter how small, no matter how far around you go in the unit circle, you will always have an x and y coordinate. So you'll always have a value for sine and for cosine. So we use this notation right here, which is the way that I write that by hand is a double bar with an R, which stands for all real numbers. You can plug in any number into the sine function and you'll always get an output. You can plug in any number into the cosine function and you'll always get an output. When you get to tangent, however, that's when things become restricted. Now, why is it restricted? It's restricted because it's a ratio. Y over x is a fraction, which means that x cannot be equal to 0. We're not allowed to divide by 0, not by some rule or mandate of the, official government of mathematicians. No, the reason you can't divide by 0 is it doesn't make any sense. You cannot take 0 a multiple number of times and end up with some other number, right? You cannot divide by 0. It is an undefined value. So tangent would be undefined anytime x is equal to 0. If you look at your unit circle, think about where x is equal to 0. It's on the y-axis. So anytime you have an angle that ends up either here with a terminal side or here with a terminal side, it's going to be undefined. For this angle, if you go all the way around to this angle, and then for any multiple of those. So if you went around all the way around once and came back to here, that would be another angle that is undefined when you plug it into tangent. Now what are those angles? The first angle I drew was pi over 2. Right, which happens to be this guy right here. The second angle I drew was 3 pi over 2. Notice 2 pi over 2 is just pi, which is fine because your y is equal to 0, but your x is non-zero. That is, if I was over here, everything's okay. But if I go all the way down to here, I got 3 pi over 2. If I go another distance around, I'm up to 5 pi over 2. If I kept going, 7 pi over 2, 9 pi over 2, 11 pi over 2, all of those would be problems for tangent. And actually, I can go the other direction as well. If I went in the negative direction, say I went down this way or around to here, all right, that's negative pi over 2 and negative 3 pi over 2, and keep going. What the result is, any odd multiple of pi over 2 is a problem for tangent. So the way that I would write that is the domain for tangent is all real numbers except any odd multiples of pi over 2. Let's move on to the next batch. Now all the rest of these, tangent included, all the way through cotangent, are fractions. So they're all going to have problems somewhere, some restriction that you cannot plug that angle into the trig function. Cosecant of theta was 1 over y. So that means that y can't be 0. So think about, where is y equal to 0? Y is equal to 0 on the x-axis. So 0, 0 here is a problem, and so is pi. 0, pi, and then if we went all the way around here, 2 pi is a problem, and then 3 pi, and so forth. Pi, 2 pi, 3 pi, 4 pi, 5 pi. Anything that ends up on the y-axis is going to be undefined when you plug it into cosecant, because you'll be dividing by 0, and that's not defined. So any multiple of pi, 0, pi, 2 pi, 3 pi, any multiple of pi at all is going to give us a problem. Either you go negative, right? So if you went in the negative direction, there's negative pi, here's negative 2 pi, and so forth. Secant of x, moving on to the next one, remember secant of theta is 1 over x, which means x can't be 0. Now, because we've already done that, we actually can just reuse the information we got from tangent. Any odd multiples of pi over 2 are going to be undefined for secant, so you would have all real numbers except odd multiples of pi over 2. And then cotangent, which is x over y, means y can't be 0. So that's the same as cosecant, meaning any multiple of pi would give us a problem. So this tells us what values we can plug into our functions. We'll revisit this in a later lecture when we come back and look at the graphs of these functions. You'll see graphs of these functions do not have a point defined at any of these exceptions or restricted points. Now let's talk about the range of these functions. Remember, range means the outputs of the function. So you think about what values you get out of the sine function or the cosine function, the tangent function, etc. Okay, now I've grouped them in a slightly different way than I did before. We'll do, actually the same order as I had on the slightly different. Sine and cosine, cosecant and secant, and tangent and cotangent. So functions and what we call their cofunctions. Now sine and cosine are the x and y values of those coordinates. Now if you have a unit circle, that is, the radius is 1, and your cosine of any angle is always the x coordinate. Look at this unit circle and find out what's the smallest x you could possibly get out of this function. The furthest left you could go on the x-axis would be -1. And the furthest right you could go on the x-axis for any angle, no matter what angle you draw in here, is going to be +1. Right? So notice the cosine would go from -1 to +1, but the same is going to be true for the y-axis, because your unit circle goes all the way down to -1 and all the way up to +1. The outputs of these functions will never be smaller than -1 or bigger than +1 by their very definition. Okay? Now on the other hand, cosecant, which is 1 over y, 1 over the sine of that function, or sine of that angle. If you take the reciprocal of a number that is between -1 and +1, you're always going to be bigger than 1 or less than -1. Right? Again, let me say that one more time. The reciprocal of a number that's between -1 and +1 is either smaller, that is less than -1, or bigger than +1. Just think about that. If you took the number 1/2, that's in this range right here. Right? 1 over 1/2 is 2. it's bigger than 1. So taking the reciprocal of a number between -1 and +1 gives me a number that's either less than -1 or bigger than +1. So because secant 1 over x, the same thing is true for it. All right. Now tangent and cotangent, y over x and x over y in here, you can actually get to any real number. So the range, one way to write that would be to write all real numbers, or I could write it using a range of values. I would say -infinity, +infinity. You can get to any output with the tangent of an angle or a cotangent of an angle. Consider the following questions. I want us to evaluate what is the cosine of pi over 3. All right, so remember from our previous lecture, cosine of pi over 3, that's 60 degrees. We use our unit circle, 60 degrees is right here. We know the coordinates of that point turn out to be 1/2 and square root of 3 over 2. So the cosine of square root of 3 over 2 is the x-coordinate of that is equal to 1/2. And the sine, by the way, is square root of 3 over 2. What happens if you look at cosine of 7 pi over 3? Now what is 7 pi over 3? If you want to see it in degrees, that is, well, this was 60 degrees. This turns out to be 420 degrees. You can figure that out by doing 7 pi over 3 times 180 over pi. You'll get 420 when you work that out, because you get 3 goes into 180 60 times. Pi is divide out. 7 times 60 is 420. Another way to see it is 7 pi over 3 is the same thing as 2 pi plus pi over 3. It's one rotation all the way around once and then plus a pi over 3. Which means that you get the same point. So the answer is still 1/2. Cosine of 13 pi over 3 is 4 pi plus pi over 3, or 2 pi plus 2 pi plus pi over 3. Notice that's one rotation, another rotation, and then plus pi over 3. You're at the same point again. What are you seeing? It's repeating itself. If I go -5 pi over 3, -5 pi over 3, I'll draw this in green, is actually the angle that goes around and ends up right there. So it is also 1/2. The same thing's going to be true of these guys. You're going to get square root of 3 over 2 every time. The reason I point this out is to identify something called the period of the trig functions, right? This means they repeat themselves. Trig functions repeat. Meaning that as you move forward, as you increase the value of theta, that is the angle you're plugging in, eventually you're going to start repeating your values. And the reason is because you're going around the circle. Once you go around the circle once, you start to repeat all the same points again. Okay? So after each rotation, you repeat the number of points. Now for any of our trig functions, if we plug in an angle, we can add or subtract multiples of 2 pi, and we'll always get the same trig function value. So for example, if you plug in theta plus 2 pi, if you add 2 pi to theta, you get the same thing as sine of theta. If you added 4 pi to theta, you get the same thing as sine of theta. And no matter how many integers you plug in and you keep adding those rotations, you're going to still end up at the same point, so you're going to get the same trig function value. Same thing goes for cosine of theta. A function is called periodic if it does that, meaning that if it repeats itself after some increase in your value that you're plugging in, so that f of theta plus some p gets you back to just what f of theta is, then we call it periodic. In other words, the function repeats itself every p units. Now the smallest value p, the smallest number that you can plug in so that this equation right here is true, is called its fundamental period. Now we know that all of our trig functions, just by virtue of being functions of angles, are going to repeat themselves after 2 pi, but the fundamental period for a couple of our trig functions is actually smaller than 2 pi. For both sine and cosine and cosecant and secant, their periods, their fundamental periods, are 2 pi. But it turns out that tangent and cotangent actually repeat themselves after just 1/2 of a rotation. They start over again. Okay? We're going to come back and use this information a little bit later on, but for now let's move on to one of our other properties of trig functions. The next property that I'd like us to take a look at is what are the signs of the I wanted to highlight that, of the trig functions in each quadrant. Now you'll remember that sine is the y coordinate, cosine is the x coordinate, and tangent is y over x. Now if you're in the first quadrant, okay, what I would call quadrant 1, Q1, then you know that x is positive over here and y is positive in here. So if y is positive, then that means your sine function is going to be positive. In terms of its output, it's going to be a positive number. Up here, x is also going to be positive, and if you divide a positive by a positive, you get a positive answer. But in quadrant 2, you have something different. X over here is now negative, and y is still positive. So notice that only one of your trig functions stays positive, right? Because if you have sine, that is a positive number because you're above the x-axis, your y is positive. But your cosine, because your cosine is the x-coordinate, you get a negative answer. And if you take a positive divided by a negative, you get a negative answer. So if you have the value of the trig function, say you don't have the angle, but say you have the value of the trig functions, you know that if the sine is positive and the cosine and tangent are both negative, then you have to be an angle in quadrant 2. We're going to use this to kind of reverse engineer some of our problems. So in some cases, instead of me giving you the angle, or instead of you having an angle and you want to find the trig function values, it may be that you have some of the trig function values and you want to find either the angle or other trig function values. But first thing you need to know is, where is that angle? So by knowing just whether or not they're positive or negative, you can figure out whether or not they're in quadrant 1 or quadrant 2, and you can keep going. Actually, using the same reasoning, you can get quadrant 3. Because down here, x is negative and y is negative, which means both sine and cosine are negative, but a negative divided by a negative is actually positive. So your tangent is positive in quadrant 3, but sine and cosine are negative. And then over here in quadrant 4, your sine, which is the y coordinate, is negative. Your cosine, which is the x coordinate, is positive, and if you take a negative divided by a positive, your tangent would then be negative. So notice you kind of have a pattern here. Up here you have all of them being positive. In quadrant 2, what do you have? You have only the sine is positive. Down here in quadrant 3, you have only the tangent is positive. And over here you have only the cosine is positive. So an easy mnemonic to remember this order, the way that I remember it, I'm always going, counterclockwise, so quadrant 1, 2, 3, 4. I remember all students take calculus. Maybe it's not a true statement, but should be. But all students take calculus is the way that I remember what's positive in a given quadrant. All are positive in quadrant 1. Sine's positive here, tangent's positive here, cosine's positive here. All students take calculus. So you can use, again, you can figure out what quadrant you're in by just knowing signs of your angle, or of your trig functions. If sine's negative and cosine's negative, what quadrant do you have to be in? Well, that would have to be quadrant 2.